Now we will see an important spectroscopy called as vibrational spectroscopy or infrared spectroscopy. Infrared spectroscopy or the vibrational spectroscopy, it involves the study of vibrational transitions. So we all know that the molecules are quantized independently according to the Born-Oppenheimer approximation, and this particular spectroscopy, it studies the vibrational transition that takes place in the molecule on absorption of the radiant energy. The radiant energy which is responsible for these vibrational transition comes from the infrared region of an electromagnetic radiation. That is why this spectroscopy is also called as vibrational infrared spectroscopy. Now, what are IR active and what are IR inactive molecules? This is the point number 1 that we will try to study. So, the first thing first is we want to know which vibrational transition will be IR active and which vibrational transition will be IR inactive. In order to show an IR spectrum, in order to exhibit an IR spectrum, the necessary condition is that there should be a change in the dipole moment, when atoms are displaced due to vibration. When atoms in a molecule are displaced due to vibration. Now you all know that in rotational spectroscopy the diatomic molecule is considered to be a diatomic rigid rotator. So microspectroscopy, the diatomic molecule is considered to be a diatomic rigid rotator. Here it is considered as a simple harmonic oscillator. What is a simple harmonic oscillator? A simple harmonic oscillator is just like, say, you on a wall you fix a spring and you fix a mass on it. So what is important is to understand the simple harmonic oscillator. If you understand this, we can understand how the molecules are IR active and inactive. So if I subject it to vibration, say if I stretch a spring, what will happen? This will be the new position. Say this is A, this will be the new position A prime. What will happen? It will go back and forth, isn't it? And at some point of time it will acquire a new position. So these are the distances. This one is, say, equilibrium distance R, this one is, say, R double prime, and this one, the whole distance is, say, R prime. Now in this case what will happen? When I subject this mass of A to the vibration, what will happen? It will undergo oscillation, and these oscillations, these are called as the motion of a simple harmonic oscillator. And how it happens? So it goes up, it goes down, it goes up, it goes down. This is an example of a simple harmonic wave, and you in nature you see many sorts of simple harmonic waves, like when you subject a spring to the oscillation, that is an example of a simple harmonic oscillator. So with these backdrop, we will try to understand what are IR active and what are IR inactive molecule. So what is the necessary condition? When atoms are displaced due to vibration, there should be a change in the dipole moment of the molecule. Now let us find out whether the homonuclear diatomic molecule like hydrogen, nitrogen, oxygen, chlorine, all these are homonuclear diatomic molecule. Homonuclear diatomic means they are made up of same type of nucleus. These molecules, you know, dipole moment. Let us consider the example of hydrogen molecule. In this particular hydrogen molecule, you know, the mu is equal to 0. Why? Because mu is equal to E into R. E refers to the charge and R refers to the distance between them. Now as the charge is 0, even if I subject it to, say, stretching, and a new position is like this, even during this case, what will happen? Charge remains 0. Even though the R changes, charge remains 0. So the new dipole moment of the molecule will be 0. So delta mu will be 0 minus 0 means 0. So all homonuclear diatomic molecules, they are IR inactive. On the contrary, if I have, say, a heteronuclear diatomic molecule, say HCl, right? If I subject it to oscillation, if I stretch the bond, the new position will be this, and the compressed would be like this. sorry, I will put H here, right? So this is the equilibrium position R, this is R prime, and this is R double prime. Now there are charges here, some E plus and E minus charges are there. So some charge is there, it means that this molecule is having mu not equal to 0, this is also having mu not equal to 0, this is also having mu not equal to 0. So certainly their delta mu will also be not equal to 0. So when the atoms are displaced due to vibration, there should be change in the dipole moment. This is the condition for a molecule to be IR active, and that is why the molecules like HF, HCl, HBr, then CO, NO, you can take any diatomic molecule having two different atoms, they will be IR active. If you consider the triatomic molecule, say for example water, when it comes to the triatomic molecule, you have to think of its geometry. Say water, you know, it is a V-shaped molecule with oxygen in a sp3 hybridization with couple of lone pairs. So having an angle of 105 degrees centigrade, the water molecule will have mu not equal to 0, and when you subject it to some stretching or bending kind of vibrations to the water molecule, there will be a change in the dipole moment when the atoms are displaced due to the vibration. So displaced means what? When the atoms acquire new position, they should have, that will be the new position, and during that position mu will also be somewhat different. So there will be change, initial dipole moment and final dipole moment should be different. If that is the case, then the molecule will be IR active. So water is a molecule which is IR active. Now I will tell you the example of one more molecule which is an interesting case, which is a linear but which is a triatomic but linear molecule, that is carbon dioxide. Now carbon dioxide, you know, is a linear molecule. So if I stretch carbon dioxide symmetrically stretch 2 oxygen from the carbon symmetrically, then again there will not be change in the dipole moment of the molecule. The dipole moment will only change if one of the oxygen comes closer and one of the oxygen goes further away. Now in this case the dipole moment will not cancel each other, because this bond moment is higher in magnitude as compared to this bond moment. So symmetric stretch, this is an example of a symmetric stretch, and this is an example of an asymmetric stretch. So symmetric stretch in carbon dioxide is IR inactive, whereas the asymmetric stretch in carbon dioxide is IR active. So this is how you can explain how the different types of molecules are IR active and IR inactive. Now moving forward, how does an vibrational transition takes place? For that sake, the next point that you need to understand is what? You need to understand what are the energy levels of a simple harmonic oscillator. So according to this, we are just trying to understand the quantization of vibrational energy levels in a diatomic molecule, considering it as a simple harmonic oscillator. Simple harmonic oscillator means which obeys Hooke's law, which is what is the Hooke's law? F is equal to minus kx. So according to the Schrodinger wave equation, quantum mechanics has given us the value as V plus half h nu, or you know nu is equal to C nu bar, and in the context of IR spectroscopy, nu bar is also referred as omega. So omega and nu bar, these are essentially the symbols for the wave number. Now what will happen? So your equation becomes EV equal to V plus half h c omega. Now what is V here? V is called a vibrational quantum number, and it can have the value 0, 1, 2, 3, 4, etc. So what will happen? You will get the different energy levels, and if you try to plot the different vibrational energy levels, the concept is very simple. We are now trying to understand, this is the equation that is to be followed for the allowed vibrational energy levels. So what we will do, we will just using this equation, putting V is equal to 0, 1, 2, 3, 4, and we will try to plot the different energy levels. In order to understand this, I will give you one pictorial representation. This graph will be quite helpful. Say I have a chlorine atom here which is bonded to a hydrogen atom. Now during this what will happen? Let the equilibrium distance at rest is r. Now when I stretch the hydrogen atom keeping the chlorine fixed, what will happen? This will undergo oscillation in this direction, back and forth, right? Depending upon how much energy I put in to stretch the bond, I will get the different energy levels. So new positions of these represents what? These points on these curve represent the position of the hydrogen when they are stretched or compressed. So this will be the first energy level, this will be the second energy level, this will be the third energy level, this will be the fourth energy level. Likewise you will find the different vibrational energy levels. This will be your V is equal to, I will write the value of V on this side and energy on this side. Okay, so this will be for the, so no need to keep this picture in mind, just to give you an idea I have put HNCl here, otherwise you can just keep this in mind. So for V is equal to 0, what is the value? For V is equal to 0, what is the value? The equation was EV is equal to V plus half, what was the equation? V plus half Hc omega, right? So when putting V is equal to 0, the value becomes half Hc omega. Then putting V is equal to 1, it will become 3 by 2 Hc omega. V is equal to 2, it will become 5 by 2 Hc omega. V is equal to 4, it will become 7 by 2 Hc omega. For the next, it will become 9 by 2 Hc omega. So this is how the different energy level, vibrational energy levels are spaced, and they are equidistant. They all of them are having the energy between the two successive energy level is the same. This distance and this distance, they are all same. So here you get an application of course this energy is in centimeter inverse. So you get an idea about how the different energy levels are quantized in a simple harmonic oscillator. Now moving next, the one important definition which is usually asked in the examination, there can be MCQ on this question, like the energy of the lowest vibrational level. What is the lowest vibrational level? Lowest, just a moment, I will just tilt the camera. Lowest vibrational level is what? Lowest vibrational level is V is equal to 0. And what is the EV for lowest vibrational level? It is equal to half Hc omega. Now what is V is equal to 0? V is equal to 0 is called lowest vibrational level, and the energy of the lowest vibrational level is referred as 0 point energy. So there is many a times there is a question on this particular part, that what is 0 point energy? What is 0 point energy? The energy of the lowest vibrational level, that is V is equal to 0, is called as 0 point energy. And what is this? It is EV is equal to half Hc omega, right? Now so these are the above picture clearly tells you about how the vibrational energy levels are quantized, right? Now you know how the energy levels are quantized. Now the next step is what? The next step is, what is the selection rule? Which transitions are allowed? Which transitions are allowed and which transitions are not allowed? So this has been depicted by what is called as selection rule. For the pure vibrational spectrum, the selection rule is delta V should be equal to plus minus 1. Delta V should be equal to plus minus 1, and means the transition that involves delta V is equal to plus minus 1, they are called allowed transition, whereas the transitions for which delta V is not equal to plus minus 1, they are called forbidden or not allowed transition. So what are the allowed transition? The allowed transitions are those for which delta V is equal to plus minus 1, right? Now how the rotation, how the vibrational spectrum of a diatomic molecule arises. Now during the course of vibrational transition, what happens? The transition may occur from, say you have different vibrational energy levels. So I will just put 3 different vibrational energy levels here. So it will be half Hc omega, 3/2 Hc omega and 5/2 Hc omega. These are the 3 different energy levels, this one and this one, right? So these are the 3 different vibrational energy levels. And what is the selection rule? The transition can occur either from here to here, or here to here, or from here to here, or from here to here. If you go up, again the same rule follows, because these are the transition, means going up or going down, means going up to the higher energy level or coming back from the higher energy level to the lower energy level. There is only a step of, there is a 1 step gap between the two energy levels. So what will happen? The frequency of the pure vibrational level, where you will get a band, so usually you will get a band. So nu bar of the spectral line that you will get, nu bar refers to what? Nu bar refers to the transition that is taking place from one vibrational level to another vibrational level. It will be given by the equation del nu bar, or you can say delta nu bar, which is equal to, delta nu bar refers to what? Delta nu bar refers to the frequency of the line. So where you will get the frequency of the, where you will get the line in the spectrum? You will get the line, say a transition taking place from say 1 to 0. This is 1 level, this is 0th level, and this is 2nd level. If a transition is taking place from 1 to 2, then in that case what will happen? You will get delta E from the transition 1 to 0. What will happen? From the transition 1 to 0, the energy would be E1 minus E0. Now what is E1? E1 is 3/2 Hc omega, and E0 is half Hc omega. The value remains to be Hc omega. So delta E from 1 to 0 will be equal to Hc omega. Now even if you have a transition from higher energy level, say 3/2 to 5/2, or 5/2 to 5/2 Hc omega to 3/2 Hc omega, again the difference will come out to be Hc omega. So you can have a transition from any two energy levels. In all those cases you will get that the energy difference would be Hc omega. Now where will you get the line? The line that you will get will be essentially the wave number of the line. If you want to get the value where you will get the omega, then you will get, notice that you know that delta E equals to Hc omega. So if you divide delta E by Hc, so if you divide delta E by Hc, then you will get what? You will get the wave number of the line that you will get. So omega oscillation, or in other words it is called as nu bar oscillation, will be equal to what? Omega centimeter inverse. So what happens in most of the cases? Normally the molecule, so you will get a spectral line at omega centimeter inverse. Whenever a transition takes place from say V is equal to 1 to V is equal to 0, or V is equal to 2 to V is equal to 1, you are going to get the line at omega centimeter inverse. So usually most of the molecules, they are at V is equal to 0. So when you draw a IR spectrum of a molecule, normally for a particular transition you get only one line which corresponds to omega oscillation, which corresponds to omega oscillation. So you get only one line in the IR spectrum of a diatomic molecule for one particular transition. So if in addition to this, sometimes the transition which are following the selection rule, that is delta V is equal to plus minus 1, they are called allowed transition, and the transition from V is equal to 0 to V is equal to 1. So you can have varieties of the transition. Here you can have the varieties of the transitions. The transition from V is equal to 0 to V is equal to 1 is called fundamental. The band that you get because of V is equal to 0 to V is equal to 1 is called fundamental band or fundamental vibration. Whereas in addition to these, there are some transition for which delta V is equal to plus minus 2 or plus minus 3. For these you get a very weak band, and such bands are called overtone bands. So for fundamental bands, delta V is equal to plus minus 1, and in addition you can get some very weak band which are called, they are weak in nature, such bands are called overtone bands. Okay, so this is how you can understand how you get for in a heteronuclear diatomic molecule, in the IR spectrum you will get only one line which corresponds to the transition from delta V is equal to plus minus 1, which is a fundamental band. One more point which I forgot to tell you about the 0 point energy, that the 0 point energy in a 0 point energy of a simple harmonic oscillator or a heteronuclear diatomic molecule is not 0, even though the name itself indicates 0 point energy, but it's not 0, rather it is what? E V is equal to 0 is how much? It is equal to half Hc omega. So sometimes people use, there are different symbols used for the wave number. Some people use nu bar, some people use omega, some people use omega bar also. So you need not have to get confused. There is one more symbol which we use, which is called as omega oscillation. Omega oscillation and omega bar refers to what? These are two different things. Omega oscillation refers to the wave number of the spectral line that you get in the IR spectrum, which is essentially the energy difference between the two vibrational energy levels. Now this is all about that, how you get a spectrum in the vibrational spectrum for a diatomic molecule. Now we will see one more point related to the vibrational spectroscopy, and that is very important, because this particular equation that we are going to see now will be very important in understanding how you can get a structural information because of the infrared spectroscopy. So let us deal with it one by one. So yet another important point that we are going to see is the relationship between omega oscillation and force constant. As I mentioned earlier, that a diatomic molecule you can consider as if it is a two atoms, say A and B, bonded together by a spring. Now when you subject this spring to the stretching, or when you take atom B away from A, what will happen? The spring will try to restore the original position. The spring will try to take it back to the original position. So what will happen? Say a new position is, say, B prime, right? So this displacement is, say, x. Okay, now there will be one restoring force which is acting over here to get it back to the original position, and that is called as what? That is called as restoring force. This restoring force F is essentially obeys Hooke's law. It obeys Hooke's law. What is Hooke's law? Hooke's law tells you that F restoring force F is equal to minus kx. F is equal to minus kx. What is k here? K is called force constant. Force constant. And how can you define the force constant? Force constant can be defined in terms of force if you convert this x into 1. When x is equal to unity, F is equal to when F is equal to unity, F becomes equal to k, or F is equal to minus k, or k is equal to minus F. So what is k? You can define from this: when x is equal to 1, F is equal to minus k, or k is equal to minus F. So you can define it like that. What is F? F is a restoring force. So restoring force per unit displacement is called force constant, and force constant is a characteristic of a spring. I can give you one example. You have handled different types of the spring, and all springs, they obey the simple harmonic. They are an example of a simple harmonic oscillator. So you know, different types of the springs are there, like this, the one that you have in your pen, like this one, right? The other, you might have seen the spring where you have seen the other type of the springs in the nature. This is one example, right? So you just see this, right? There is a one spring inside this pen, right? I can show you. And this spring is again a spring which can be easily pressed or stretched by the finger of a human being. But if you consider some harder spring, for example, the shock up you have in your two-wheeler, it again has a spring. Then again you consider a spring that has a shock up, say Volvo buses are there, right? In Volvo buses you have a very strong spring, isn't it? So that will not, so every spring has got different force constant. So force constant is a characteristic of a spring which can be correlated with the force constant, can be correlated with the strength of a spring, right? Strength of a spring. So force constant can be correlated with the strength of a spring. So this omega oscillation and the force constant, they are related to each other by an equation. Omega oscillation is equal to 1 upon 2 pi under root of k upon mu. What is mu? Mu is reduced mass, which is equal to m1 m2 upon m1 plus m2. So omega oscillation and the strength of the spring, they are the two important parameters. So if you solve this equation, and if you take omega square is equal to 1 upon 4 pi square k upon mu, or k is equal to 4 pi square omega square mu. So you can get here one clear cut idea that when you have, you can write this equation in terms like this. This is the equation that you can get in terms of k equals to 4 pi square omega square mu, where mu is the vibrational frequency, and when you convert it into the wave number, because omega is essentially the frequency in hertz, right? So if you convert it into, it is in terms of hertz, but when you convert this particular equation in terms of wave number, you have to divide by one more term. The equation will become 1 upon 2 pi c under root of k by mu centimeter inverse. So this equation, the final equation that we have written so far, can again be rewritten in another fashion, and that is k equals to 4 pi square omega square, then of course you have to get c square and then mu. So we have added one more term, that is c square here. These are the two important equation, and this is the equation which is very very important while solving the numericals based on the IR spectroscopy. So once you get the IR spectrum will give you the information about the omega, and once you get the information about the omega, you can calculate the force constant of a bond. And it has been noticed that there is a relationship between force constant and the strength of the bond. For example, I'll give you one typical example. Say carbon-carbon single bond, carbon-carbon double bond, and carbon-carbon triple bond. Which one will be the stronger? This will be the carbon-carbon triple bond will be the stronger, and carbon-carbon single bond will be the weakest bond in this series. If you compare the force constant, the unit of the force constant is K is Newton per meter. The value is roughly around 500, 1000 and 1500 Newton per meter for these bonds. So these clearly indicates that these are the bonds with, so if the strength of the bond increases, the force constant also increases. So there may be an MCQ that arrange the following bonds. You may be provided with 2-3 bonds, and you are asked to you may be provided with 2-3 bonds, and you are asked to just a moment, and you have to ask to arrange those bonds in the order of decreasing force constant or increasing force constant, right? So if someone asks you to arrange it in the increasing order, you will arrange it like this, that carbon-carbon double bond is having lesser force constant than double bond, which in turn is having lesser force constant than triple bond. So there may be a sequence like this. So you may be given MCQ and you will be asked the correct order of the force constant is carbon-carbon double bond, then carbon-carbon single bond, and then carbon-carbon triple bond. The correct order is what? Carbon-carbon triple bond, then carbon-carbon double bond, and then carbon-carbon single bond. So there can be an MCQ based on this particular question. So this is all about the infrared spectroscopy. I will share the lecture notes. I will share the numericals as well. We will solve the numericals once we finish the Raman spectroscopy. So probably tomorrow I will share a lecture, video lecture on Raman spectroscopy, and then we will solve the numericals. So maybe 3 or 4 lectures from now we will be done with our unit. Thank you.